All right, so what I've had you guys do in your workbook is review how to classify, how to name polygons. Now keep in mind, it is just like what's going on in our classroom. If I classified you guys, I could say all the girls over here, all the boys over here. But then each of you have a name, right? So when I'm identifying something, it's a name. I'm not like, hey, you girl, right? I call them by their name, right? So polygons are the same. We name them. And so we'll look at the answers to those in your workbook problems. And then how do we use polygons? And that's really the big jump in this lesson is we look at what a polygon is, but now how do I use it? And I use it for measurements, specifically area. We have an area of a triangle. We have an area of a rectangle or a square, area of a trapezoid. And then we're also going to talk about Pythagorean Theorem, which tells us about parts of a right triangle. I want to emphasize these relationships only exist for the shapes in which they're defined, right? This relationship doesn't exist for a square. It only exists for a triangle. This relationship only for a trapezoid. This relationship only for a right triangle, okay? And so when we talk about English, you know, yesterday we talked about relating, like we're translators, we're translating English to math, right? Well, in English, don't we read left to right? Yep. In math, we don't. I can use this relationship for a number of things. This is a relationship that relates area, base, and height. And so I can solve for any of those three. It is not just an area formula. It can be a base formula. It can be a height formula. And we've got to look at it that way. All it is a relationship between three things. Right triangle, Pythagorean theorem. It is a relationship between all three sides. It is not focused on just one of the three. Okay, I had a student last class say, we just use them backwards. I love that. It's exactly right. We just use the formulas backwards because we don't have to use them left to right. Any questions on just that concept? Because that's what we're going to practice today. All right, then let's go to page 13 in your workbook. And let's talk about these first two problems, okay? All right. So let's see how you did with naming versus classifying, okay? Naming versus classifying. All right, so the names of this polygon is that it is a pentagon. That is the classification. It is not the name. It is the group, the classification. All right, someone tell me, what do you notice about the names? The names of this hexagon.
They're starting at different points.
They're starting at different points. But now someone pick up on her thought there. They start at different points, but then what happens?
They all follow the same order.
They all follow the same order. And that's really, really important. Because what this name tells us is that AB is a segment that makes up this hexagon. Right? It is not AD. AD will never be part of the hexagon. It's a diagonal, but it is not what makes up the hexagon. Okay? That's really important with naming of polygons. Notice the name of this is not hexagon. That is the classification. Questions on one or two? All right, let's go and see how you are at drawing. Messy. All right. Now, I will never grade you on how perfect it looks. I will grade you on the properties that you're able to show. Okay, so this property here shows 8 segments. Someone tell me, what does it mean to be regular? Because you had to define that yesterday. I had you write it in your notes. What is regular? Tell us, Josh.
Isn't it like on all sides and angles?
Keyword he used, and. All sides, same measure. Now mine's not perfect, but it's close enough. And, keyword and, all angles are the same measure. That's what it means to be regular. It is not one or the other, it's both. Okay, so there should be a distinct difference between this drawing and this drawing. You obviously see the symmetry here. Here, there is no symmetry because of the directions. All right, so let's go 5, 6, and 7. And this is what I was alluding to before. Now we've got these polygons. Let's figure out how to use them in measurements. So you have already written down all of these formulas. So our first task is what formula do I need? And then my second task is how do I set up the problem? I really could care less what your answer is, as long as your process is correct, because we can tweak the calculation part very easily, okay? All right, so what is the height of a triangle with a base of 4 and an area of 14? First thing you've got to know is that a base and a height always, forever, always, with every shape, there is no exception, base and height always form a right angle. Always. So you never should be asking, wait, where's the height? Because you got to find where the right angle is formed. And then you can say, this is the base, this is the height. Okay? All right, Patrick, which relationship are we going to use? Yeah, absolutely. Area of a triangle is 1/2 base times height. Now, in this problem, which variable are we solving for? The height, because that's what we're asked for. So there's 2 ways to do this. I have a tendency to think you're going to like the same way that I like. You remember in algebra, they used to make you solve for the variable? They didn't tell you numbers. You solve for the variable. That's not really usually that popular. I prefer to plug in numbers first and then solve, because it's easier to work with numbers than letters, okay? So I'm going to suggest to you that you take area as 14, so I put it in there. Base is 4, so I put it in there, and I'm left with height. The only reason I use parentheses is just to organize myself a little bit better, okay? Be okay with just why I put numbers where I did? Please follow my lead. Practice this skill means you should be writing. Now, I will be your calculator. Okay, so 1/2 of 4 is 2. So do we agree the next step is 14 equals 2h? Everyone comfortable with that? And so what is h? 7 what? 7 meters. Thank you. So notice, area is meters squared, because area is a base times a height. A meter times a meter, which is meters squared. So height has to be just 7 meters, okay, not meters squared. What questions do you have in solving this? You comfortable with this? All right, what about here? What formula am I going to use for number 6? Good, good, Daisy. So we have length times width. All right, so area is length times width. That means we're solving for area. So I'm going to say area is 4 times 6. And so what is my answer? 24 what? Squared. Thank you. Because this is area. Ooh, that's messy. I got a little fancy. Is that right? Now, when I ask you questions, think about, okay, you got homework due Friday. This is Wednesday, no homework on Wednesdays. You got homework due Friday. When I say, are you comfortable? Like, could you do this by yourself without my prompting? Like, does it make that much sense? Okay. All right, what about here? This one has a 2-step process. Anybody help walk me through how to do this? Where would we start? Start us off, Max. What you got?
Okay, so you would square root of 36.
Okay, you're jumping ahead of us. Yes, you're correct. You're 100% correct. Let's back up of why he's doing what he's doing. Okay. So do y'all agree that we're looking at a square, right? What is the formula for the area of a square? Length times width. Well, if it's a square, do you guys agree that side times side? Because isn't a square, the length and the width are the same?
Yeah.
So are we okay saying S squared for the area? What is perimeter?
All of the sides plus each other.
Okay, good. And so all the sides for a square are the same, right? So anybody tell me what that formula would be? Condensed? Don't think of numbers, just a generic formula for the perimeter of a square. Thank you. 4 sides. Does that make sense? Because Patrick told us it's side plus side plus side plus side. Wasn't that 4S? We good there? Okay, so what you did really well is said, okay, we have a perimeter problem and it gives us area. So I've got to use those 2 formulas. Now, where Max went, he skipped about 4 steps on us. Great job. Is that area given in the problem is 36. And if you heard what he said I got to take the square root of 36. So do all of you know that how do we undo a square? We square root it. That's this button on your calculator. Basically, what you're saying is what 2 numbers multiply to give me 36. Well, if we don't know that just off the top of our head, we would have to take the square root of 36 so the calculator could tell us what that number is. And so hopefully we all know the square root of 36 is, yes. So now we know S is 6. But did the problem ask us for the side length? No. What did it ask us for? Perimeter. Addison, what would you do next? Thank you. I take the 6 and I plug it right into what I did. Now, please take note. Didn't I do a setup first so that I know where I'm going? That is so important to being a problem solver. That is so important to thinking mathematically. You guys are you have such a habit. Just let me solve the problem. So at this point, you think you're done because you don't have a plan of what's next. That 30 seconds of what do I need makes this seem so simple because the calculations really will never be that difficult in geometry. The plan and the setup will be the difficult part. Okay, what's your question?
Couldn't you just take 36 divided by 4? Just like add that, like.
Let's talk about why we can't. So our answer is 24. What's the perimeter? Inches. Okay, and so that's our perimeter. Now, a great question is, can't I just divide 36 by 4? If I did that, wouldn't I get 9? Okay, and what I would be saying is that side length is 9. And the reason we can't do that is because this is an area, and an area is 2 numbers multiplied. So then I couldn't divide by 4 because 4 isn't related to the area problem, right? It's 2 numbers that are being divided. Does that make sense? Questions on this? All right, you guys, take a second and read this. We're going to use this as an example before we go back to a problem in your workbook. Okay, so take a second to read what it is that we're looking at. All right, so what our task here is to take this island and figure out what is the area. So do we have enough room for these birds or not? Is the population of the birds growing? All the things that we would need to calculate using an area. Now, what is the problem here? It's not a real shape, okay? We don't have just like a formula to throw in this. It looks like a dinosaur. Anybody else?
Yeah.
Okay. So we don't have a dinosaur area formula. Okay, anybody else see something different? A dragon, wings. All right, anyway, so what is it that we can do with the information we do have to find the area? So it's like our analogy of the connections we did the first week of school, okay? Here's what we know for those formulas. Here's what we have. How do we connect the two with something that we can use here? Any suggestions? What can we do here? Excellent. We use the shapes we have to fill in our dinosaur. What shape does that look like? Okay, now if we use a model, is a model going to be perfect? No. But a model is used all over real life to counter costs. Think about what it would take to find the actual area of this versus what we can do with just other shapes. Is the approximation that big of a deal compared to the effort it would take to find the exact area? No, no. It's like anyone would realize that, right? And so that's why models are so valuable. They're not exact, but they're sure close enough, okay? All right, so here we got a triangle. What do we think this is? Square. Now, in my last class, someone said a circle. Is a circle a polygon?
No.
No, okay? It is not a polygon. So specifically here, we're going to talk about polygon. Now, we'll correct our language a little bit here. Is that a square?
Yeah, no.
Rectangle. Rectangle, okay? It's a rectangle. All right, and so we've got a triangle, which we know the formula for. We've got a rectangle, which we know the formula for. And then what are we looking at over here? Probably another triangle, okay? Now, of course, we're going to need to find these measurements, but we have a scale to do that, okay? So this would be a use of our polygons, is to take them to model different scenarios, because we have enough of them that could be really good models for something irregular like this. All right, take your workbook, go to page 14. I don't want you to draw anything yet because I want us to have the same model. But look at number 10 and think to yourself, without drawing on it, what would be a good model for that shape? Think about what you could actually use. So this is a park. And let's think about how could we model this park? Yeah, don't draw it yet because I want us to draw the same one for calculation purposes. But here's what we're looking at. So before we draw on this, okay, what potentially could be modeled using this top little part? Triangle. What about this middle part? Rectangles, okay. What about this bottom part? Let's do a trapezoid because does it come to a point here? Right? Not so much a point, okay. And so we're going to use a trapezoid. Now, I already have the dimensions. Max, you got a question?
I have another one.
What do you got?
So you split it vertically, like right there, yeah. And it's a rectangle.
I like that suggestion. I might suggest a trapezoid over here just because this doesn't come to a point. I like that idea. Now, I would like to use the triangle, rectangle, trapezoid model because I already have the dimensions and I want us to practice all getting the same answer for area, okay? So if you would take a second and create that model. So the triangle has a base of 7 and a height of 3. The rectangle is a 12 by 7. And you see the trapezoid that I drew. So if you would recreate that so that we can do accurate measurements. Once you get your model drawn, I want you to find the area of each of those. What are we going to do when we find the area of the triangle, rectangle, and trapezoid? To find the area of what?
The part.
The part. So once we find all three areas, we will add them to get the area of the park. And that's what I want you to work on right now. All right, so let's go through our calculations. The answer should have been 126.5 yards squared. Okay, yards squared. So let's talk about where our answers are here. All right, so we start with the triangle, or at least I did. Area is 1/2 base times height. Base of your triangle is 7, height is 3. So we use the entire base and the height. Again, what do the base and the height always do?
Make a right angle.
Make a right angle, thank you. And so we can recognize what the base and what the height is. Same with our trapezoid, people, right? Base, base, height. So we know it's the height because it forms a right angle with the base. All right, so here we have 21.5 of that. Let me say that a little better. Half of 21 is 10.5. This is not the distributive property. I do not take half of 7 and half of 3. Remember, the distributive property would be like this,
Wouldn't it be for
right? It'd be 3 and then like 7 plus 3. Then I distribute, right? Not when I multiply. I just multiply 3 numbers. All right, so square is 10.5 yards squared. Rectangle, I think we're all good. Length times width, 12 times 7, that's 84 yards squared. And now we have the trapezoid. This one is probably new to you, but we follow the relationship. Height is 4. We know that because it forms a right angle. It has 2 bases, but they're being added, so it doesn't matter which one goes first. So I've got 12 and 4, 4 and 12, I add those, and I divide by 2. Now, what we know mathematically is I always do what's inside the parentheses first. So I've got 4 and 12, 16 divided by 2 is 8. Everybody with me there? 8 times 4 is where I got the 32. Now, I need to try to convince you of this, okay? Notice, lots of work there, right? But we had a plan. So it didn't feel like I was just lost at every stop. Because I knew I have to find 3 areas. And then I knew I needed to add those 3 areas. So when we know the plan and what's next, I can stick to that and not feel like I'm just lost with a big math problem. And that's my big encouragement to you as we try to develop problem solvers is put a plan in place. Don't just go to work. What are you doing so that it's purposeful? Question.
Where'd you get the numbers from?
These? Just the model that I set up. So if I let all of you do that, we would have had 22 different answers, and I didn't want that because I wanted to know you were right. And so you could have set up any model you wanted with any of these dimensions. Okay. All right, last question I want to go to is one more relationship we haven't discussed today. So let's look down at number 12. I know you have done Pythagorean Theorem before. And I want you to put it in this group of relationships that we've learned today, that it is simply just one more relationship that deals with our polygons, okay? And so here we had a relationship that was triangles. Here we had a relationship that was rectangles or quadrilaterals. Here we have a relationship that just deals with trapezoids. This is simply a relationship that just deals with right triangles. Is a right triangle a polygon? 100%. Made of 3 segments, has 3 vertices, 3 angles, it's closed. Yes. Okay. So when it deals with only right triangles, the right angle is the focal point. And so the relationship tells us we have 2 legs, A and B, that make the right triangle, that make the right angle. Okay. So those 2 legs, leg squared plus leg squared equals hypotenuse. Anybody know where to find the hypotenuse? Where is the hypotenuse always located? Anybody know? Okay, so the hypotenuse is the side opposite the right angle. Always, always, always. Okay, so if you're struggling to remember this, it's leg squared plus leg squared equals hypotenuse squared. So that's the way some students remember it as well. All right, so let me show you how this applies. Can we use it for every triangle? No, only right triangles. All right, so here we're told we have a building 195 feet tall. Isn't a building always vertical?
Yeah.
Okay. Shadows, aren't they always on the ground? Okay, and isn't a building and its shadow always perpendicular?
Yes.
Now, I know there are exceptions like the Leaning Tower of Pisa. We're not talking about exceptions. Most of the buildings in the world are vertical. All shadows are on the ground, so they're horizontal, okay? So it is a safe assumption that vertical and horizontal always form what? A right angle, okay? That is a safe assumption. And so we have a right angle, we have measurements, and we want to know how far little Colin is from the top of the building. Got it? And so that would be the measurement of the hypotenuse. Does that make sense to you? So what is the only relationship we know that relates the three sides of a right triangle? It's the Pythagorean theorem. The Pythagorean theorem is over there on my wall, so you can see it right there to the right of the polygons. And so we have side squared plus side squared equals the hypotenuse, or the unknown squared. So this is simply in our calculator, right? So I'm your calculator, there's what we would get. Everyone writing this down? Because you're gonna have Pythagorean theorem problems for homework. Homework's not due till Friday, but you still have these problems to practice. Or to have this to show as an example, okay? Now you've already shown me this once today. How do I undo a square? And there's that symbol. So I would simply put in my calculator, square root of 38,809. And out would come the number 197. So that tells me that little Colin is 197 feet from the top of the building. Does that make sense to you? Questions on that setup? We go with that? All right, real quick in summary, we're going to start a lab tomorrow, and the lab is going to have us do some more measurements. So remember, we always go to this place. We learn some things about objects, lines, angles, vertices, polygons. And then from learning those objects, we've put them to use. We are not just learning random facts. We are learning about objects that we can apply to real life situations. And that will be the way our units go all year long. We learn about objects, and then we figure out how to use them to apply to a situation. And that's why we talk so much about thinking mathematically, because the only reason we're learning about the object is to apply it to something. In this case, we used it as a tool to measure, right? To measure different irregular shapes, okay?